Now I am going to explain a little bit about the value of lambda r and lambda p, not lambda but lambda p in table 2.1, the meaning. So the elastic buckling strength of an actually loaded steel plate element can be determined by using this equation. So for example, here we have the steel plate, okay, steel plate element. It is fixed condition. It is fixed condition and it is free side, or in this case it is simply support condition and it is free surface. Then under the compression, okay, under the compression, then the section has thickness of T and the width of B. Then here stress elastic buckling strength, okay, elastic buckling strength, FCR equal to this equation. Here, what is E? E is elastic modal load, okay, so very easy. And B and T, you know. Then here, nu is Poisson ratio, okay, Poisson ratio. What is K? K is buckling coefficient. Buckling coefficient. It depends on the boundary condition. Okay, so for example, this is boundary condition and different boundary condition. Different boundary condition has different value of K. If FCR equal to Fy, if FCR equal to Fy, because we want in compact section, okay, in compact section, we expect that FCR equal to Fy, okay. We expect FCR equal to Fy in the compact section. And we have E of the material and nu equal to 0.3 for steel. Then we have B over T, this is lambda, okay? Lambda equal to this one. We use this one from here, okay? From here, then we have lambda equal to B over T equal to Fy. Okay, Fy, let's say 36 something, and multiply by this one. We have B nu equal to 0.3 here, and then divide by K. And okay, no, this one divide by this one, okay, and K, and this one equal to 3.14 something. Then we have E here. Then finally we have this one. It is for compact section, okay, compact section. So for compact section, lambda should be equal to or greater than 162 multiplied by the square root of K divided by Fy, and K depends on the boundary condition. For residual stress section, okay, you know residual stress section, okay, section has residual stress and imperfection, the column with imperfection, okay. For fixed case, we have B over T lambda equal to, it is because of residual stress and imperfection, okay, multiplied by the original equation as a previous explanation, right? Equal to this term multiplied by this term, we have 94. And if, for example, K equal to 4 for fixed, okay, K equal to 4 for fixed, fixed both sides. Then we have b divided by t equal to 188 divided by square root of f5 fy. This can be approximately equal to this one. So for practical design, we can use 190. Okay, replace the value of 188. So in the practical design, we use this one. It is approximate value of the compact section, compact of lambda b. Okay, lambda p. You can see more in the textbook for different condition. Okay, different structure and different condition, and also different boundary condition. Then we have different of lambda p. Okay, different of lambda p. You can see more in the textbook, but I try to explain for you to understand what is meaning of the lambda p for compact section. And now I hope that you understand that very clearly, right? It's very simple. So it depends on the several conditions. Okay, so now I'm going to show you some examples on the design and analysis problem. First, I am going to explain example for design problems. Okay, example 2.10.8 in the textbook, and you can also check in the textbook for this example. Let's consider a simple beam. Okay, simple beam. The length of the beam is 50 feet, and the load A here is 34 kg per feet. Bending. Then the beam has I section. Okay, the I section. We only have this section. Okay, so now unknown is TF, TW, and B. So three unknown, and we have to determine three unknown. Okay, so here we go. Okay, so this section, this problem, this structure use A36 steel. It's very simple to determine the shear diagram and moment diagram, and you also can determine this value very easy, right? So let's say here equal to 34 multiplied by 50 square over 8, something like that. Okay, so we have mx first. Mx equal to load multiplied by length square over 8, simple, right? And here we have 34 multiplied by 50 square divided by 8, then equal to this one. Keep fit. Okay, keep fit. Then based on the moment, maximum moment, we can determine the requirement of plastic section modulus. Plastic section modulus equal to m max divided by pi b sigma y. What is pi b? Here. It is due to it is beam for beam problems. Okay, for beam problems. Then this is moment mx, and 12 means it is transfer between feet to inch. Okay, this is we transfer from the keep feet to keep inch. Then because of this sigma y is 36 in inch unit. And finally we have the requirement of the Z, the plastic section modulus equal to 3935 inch. Note that I already mentioned, okay, in AISC design code, no reductions at MPS as long as V smaller than PP or tau smaller than tau Y. Okay, I already mentioned before, right? Then the second condition is V. We have Vmax equal to WL over 2 or equal to this one, okay, 850 kip. Then what is the effect of V and which part of the section observe the shear force? The wave, okay, the wave. So the shear force, only the wave is observed, the shear force. Then we have AW mean, the requirement section of the wave only, okay, because in the I section, it is assumed that only wave, okay, only wave carry the shear force. And we have AW equal to V max divided by pi V multiplied by tau Y. Pi V equal to 0.9, tau Y equal to 0.6 multiplied by the sigma Y. Okay, this is sigma Y. And finally equal to this one. This one is requirement of the section of the wave. And now because we have the width of section, then it's easily to determine the requirement of thickness of the wave, right? Yes. TW equal to AW divided by 60. This one. Then the requirement is 0.728 or for construction, component of construction, we can use 0.75, and this value is 0.75. Okay, and we can use this one. So now TW equal to 0.75 or equal to 3 over 4. Now we still have two unknown, B and TF. Now we have to consider also the wave local buckling check. Okay, we have to consider also the local buckling of the wave. This wave have to check. You have the W divided by TW, the width divided by the thickness equal to 80. And compared to this one, so please check in table 2.1 in the book that I already explained. I already talked about, right? And check in this one, and we can find the wave. For the compact section, this value lambda should be smaller than or equal to this value. Okay, and this value equal to this, and we found that it's okay, good. So you can go further. Okay, this is wave in flat compression in table 2.1. And the requirement of plastic section modulus G should be equal to this one. Okay, should be equal to this one. In the previous, we already determined the requirement of G. And now G of the section, okay, of the section, of this section, G can be calculated by this term plus this term. This term is for flank, okay, so B multiplied by TF and multiplied by the distance between this middle, from the middle of the upper flank to the middle of the bottom flank is equal to this one, right? And this term is for the web, okay? And we have the dimension of the web already, then it's equal to this one. So now we have this first equation, a function of B and TF, okay, equal to this one. And the second condition is local buckling of the flank, okay, this is first condition. And the second condition is the local buckling check for the flank. Okay, we have to check the condition of the flank, the local buckling. It should be compact section, right? It can't be compact section. It means B divided by 2TF. B divided by 2 equal to this. Okay, it is B divided by 2. Then divide by TF. It is lambda of the flank. Should be smaller than this one. This one is for the non-compact section of the I section, okay, of the flank. And you can check this value also in the table 2.1 in the textbook. And this ratio equal to this one. We use 36 steel. And lambda should be smaller than this one. So it is second condition. Okay, second condition. So we have two equations with two unknown. Two equations with two unknown. Then we can solve very easily, right? We can solve very easily. Then, okay, from this equation we can shorten it. This equation can be shortened. Becomes B smaller than this one. Okay, so it's simple. 2 multiplied by this part equal to this one, and TF here. So then you can check to this one. Then we try B equal to. You can check. You can try every value. Okay, you can try every value 20 or 18 something. It's all fine. It's good as long as B smaller than 21.66. Okay, but if it's too small value, so it's not good. But you can try as long as B smaller than 21.66 TF. Okay, now because we have this equation, from this equation and try T equal to TF. Sorry, what is this one? B equal to 15 TF. Then replace B to this equation, then we have the function of TF. Okay, the function of TF. Then you can solve this equation. Then we have TF equal to this one, 1.87. For design, you can use maybe 2. Okay, 2. TF equal to 2 inch. Then with TF equal to 2 inch, then B may be equal to 28. So it is noted that you can assume your value of B, the ratio between B and TF, right? As long as it is compact, compact section, right? As long as it is a compact section, you can assume different value. So because of that, different assumption ratio show different the solution of the section of the flank. Okay, different solution of the dimension of the flank. So you can assume, but that assumption depends on your experience. So in the practical design, you should design and you have experience, and at that time you know which value should be the best choice. Okay, the best choice, because in the design there are many conditions, there are a lot of requirement condition. Then you have to be to consider also that condition. Okay, not really real condition of the construction. Then beyond that, you can choose the different ratio of the section dimension to show the best solution for the design structure. Okay, so it is design problems. Finally, we can determine there are three dimension, three unknown the problems. Okay, so now we have solution of TW and TF and B. So let me make a conclusion. So from now on, when you design or analysis the section, not only consider the strength of the section, okay, not only consider strength of section, but the compact or local buckling of the section should be also checked. Okay, should be also checked. If you forget to check the local buckling condition of the component of the section, then your solution has no meaning. Okay, because you cannot ensure if it can obtain the full plastic moment or plastic strength of the section or not. So please be careful. From now on, please consider also the local buckling condition of the section. Okay, remember.